Hello everyone. Welcome to the lecture hall of RIGHTINT adhesive labels. I am the RIGHTINT R&D. First of all, we need to understand the meaning of what we are doing. The meaning of this business. We are not just making adhesive labels. The business we are engaged in is to add more beauty, add a more beautiful color. That is, the self-adhesive labels can carry more information about the items and more colors. So all of us here can add color to the world. So in this industry, what we need to pay attention to most, it is a professional. Professionally is actually a polymer material. High polymer materials. What are polymers? Macromolecules are divided into natural and synthetic, with a large molecular weight. What are the ones we see in our daily life, such as our skin, hair, and some fibers? These are all natural and synthetic polymers. So the definition of polymer is actually a combination of small molecules are combined together to form a molecule with a relatively large molecular weight. From a microscopic perspective, it is actually a macromolecule. So what we use is actually synthetic. Synthetic polymers, because there are few types of natural polymers. So we use synthetic polymers. There are three main characteristics of polymers. Three forms. There are three forms. One is glassy state. One is the rubbery state. One is the viscous flow state. All polymers have these three forms. Possess these three forms at different temperatures. Take our adhesives and glues as an example. Under what conditions does it present a glassy state? What is the state of the glassy state? As the name suggests, it is similar to glass. It's hard and brittle, it loses the stickiness of glue, and has no characteristics of glue. So this one, it has a term called TG glass transition temperature. Below this temperature, it is in a glassy state. So in our TDS, why do we write its minimum use temperature, such as -20 degrees, or even -40 degrees? So in different cross-linking agents, its TG, the glass transition temperature, is also different, which is the lowest temperature at which it loses its adhesion, is different. For example, hot melt adhesives or frozen adhesives, their glass transition temperature is very low, can be as low as -40 degrees, or even -60 degrees, which can be used in some frozen environments. Glass state. It becomes brittle. If there is some vibration during transportation, it will crack. The most reasonable and best state of the adhesive. It is in the rubbery state. In this state, this is our normal temperature, or a little higher temperature. In this state, it is elastic and sticky at the same time. This is a piece of rubber. This is our normal temperature. Before coating, it's in a block. It has elasticity, resilience, and certain toughness. It has a certain stickiness, so when it is used normally, in this state, it's in a good state. Then the temperature is raised again. When the temperature is raised to the viscous flow state. Viscous flow state, it's a viscous state and can flow. This is our hot melt walking method. When the temperature reaches 180 to 100 to 200 degrees Celsius, it is in a liquid state. It can flow and can be coating. In this state, the maximum operating temperature of our TDS. Some of our TDS is not the highest operating temperature. At this temperature, it has strong fluidity. For example, hot melt glue. When hot melt coating, as it is heated, its fluidity is very strong. Its holding power will decrease, which is its holding adhesion. It will be easy to fall off when you label. It doesn't guarantee its stickiness at high temperatures. This is why in our TPS, why we set an upper limit temperature for use. The upper limit temperature of hot glue is 60 degrees, 80 degrees. Of course, for water-based and oil-based adhesive, the use temperature is relatively high. But why? We'll talk about it later. What if the temperature goes up? It reaches a decomposition temperature. When it reaches the decomposition point, the process is irreversible. That means the glue has deteriorated. When it is in a rubbery state and viscous flow state, that is to say, within the range of RTDS, it can ensure its viscosity. For a long time, it won't change. Let's review the previous lesson. Next, we will talk about the main content of the second lesson. In the second class, we will talk about surface energy, or surface tension. This class is also very important, and also for our glue bonding, including printing bonding, the most fundamental core theory. Surface energy. Or surface tension. The surface of an object has a certain amount of energy, or surface tension, like water. Why can spiders walk on water? In fact, there is a tension in water, including solids. They also have a certain tension. For solids, we are more accustomed to use surface energy. Now, let me show you a small experiment. This is a glass plate, and this bottle is water. I drop a drop of water on the surface of the glass, and it forms a hemispherical shape. Then let's look at another liquid. This is the solvent ethyl acetate. Okay. I drop it on it. As you can see, the wettability of the two is different. That is, their surface tensions are different. For glass, the glass has a higher surface energy, and its polarity with water is also relatively high. So it forms drops on the object, the liquid droplet on the object. It has a microspherical shape. Compared to solvents, oily substances are more easily wetted. That is, it has a large contact area with the object. Is there a way to accurately measure it? There is a method called contact angle. Contact angle. Contact angle is a standard test method. A drop of water is dropped on an object to be tested, including our film, or other objects, such as a plastic plate. After it is dropped, it forms a spherical or hemispherical shape. The tangent line. The tangent line and the horizontal line forms an angle. The contact angle. When the ball is more round, the smaller the contact angle is. Another case is when the wetting effect is good. This is the case. The contact angle is large. This is a more ideal state for us. It's the same with adhesives. You can also think of adhesives from a microscopic perspective. It actually has a certain amount of liquid state when it is connected to the adherent. Wetting property, good or not, determines the strength of the bond. The same is true for printing. Why do some prints need to be coated with a coating? If the coating is not applied, is to increase the surface tension of the film. For some PP have very low surface tension. So when printing, if the ink is not coated, it will be in this state. The print will be very uneven. After coating, it will be very smooth. It will be printed flat. This is the most important theory. Another thing we need to remember is, for common objects we see every day, The order of surface energy from high to low. For metals, such as stainless steel plate or copper plate, the surface energy of copper plate is relatively high. Then comes the glass plate. Glass surface energy is also relatively high. Then comes acrylic. Then epoxy resin. Epoxy resin. I guess you don't know what it is, which we often use. Epoxy floor paint. The green one, or that color, epoxy resin. Epoxy resin. Its surface energy is also relatively high, and it's also easy to bond. Why is steel plate and glass plates have epoxy resin with high surface energy? And then further down, acrylic plate. The surface energy of acrylic plates is also relatively high. Like this one we are using now, is also a very common type of plastic. And then ABS. ABS is also a common plastic. Many containers also use it. Then down, PP, PE, and you can add a PVC in the middle. PVC is about 34, PP is about 30 to 32. PE is 38 to 30. The numbers I wrote here, this is measured by our printing pen. The lower the number measured by the printing pen, the lower the surface tension. That is to say, when the glue sticks to it, or when the ink is printed, the less likely it is to be wetted. It's harder to stick with glue, and the adhesion of ink printing is worse. So the common ones here, the glass steel plates commonly used in labels, are all very easy to stick. And other plastics. The more common ones are PP and PE. What is it? It's often used in medical products like syringes, and also used in food. PP and PE are also very common, such as oil drums, and other things like this. Why do we test? We use steel plates to test. For example, it's 10 newtons of viscosity, but not PE. But it doesn't seem to stick. Why? This is because its surface tension is low, so it may only be 3 newtons. Is there a way to make it stick better to PE? So what should we do? We choose to use hot glue. Why is hot glue good for adhering to PE or PP? In fact, there is a very key word here, which is called like dissolves like. That is to say, hot glue and PE have similar polarity, and surface energy are close, and they will be well wetted together. If you use acrylic, acrylic is at 36 or 40, which is what we call acrylic. The commonly used water-based and oil-based adhesives are acrylic. Its surface energy is relatively high, so it has a strong adhesion to steel plates and glass, but less for PE and PP. Then next time we will talk about this, why it has adhesiveness. Now many polymer materials, not all of them are sticky, but are adhesive, make them sticky. There are many other factors that affect it. So everyone must remember, The theory of surface energy. And like dissolves like. That is to say, when you communicate with customers. If he uses more PE, we must first recommend hot glue. Of course, we should also take into account hot glue. It has poor heat resistance because its nature determines its performance. It will not last long. Let's talk about it in detail. Why is the composition of hot glue closer to PE and PP, but different from acrylic? The main component of hot glue is rubber. Artificial rubber. The structure of artificial rubber is actually polyvinyl chloride based. Its surface layer itself is relatively low, which is relatively low, and PE and PP are also polyolefins. Their structures are very similar, which are like dissolves like. They look very similar, and they are easy to stick together. Then add some tackifying resins. Tackifying resin and some naphthenic oil. Okay. And some antioxidants. These three ingredients are the main components of hot glue. Rubber gives it its strength, elasticity, cohesion strength. Tackifying resin is responsible for increasing its viscosity. With tackifying resin, for example, if you don't add tackifying resin, the rubber's viscosity may only be 5 or 10 newtons. The addition of tackifying resin can reach 20 or even higher. Tackifying resin actually contains some polar groups. There are few polar groups in rubber. Then naphthenic oil is for toughening. After adding these two, it will become harder. Then naphthenic oil is to increase its flexibility. But naphthenic oil also has some disadvantages. For example, naphthenic oil and PVC material. There will be some weak changes between them. There are oily substances in it. PVC has plasticizers, which is also similar to oil. Over time, both of them will ooze out. That means if you use hot glue to stick PVC, after a long time, it may lose its stickiness. The oil will ooze out. It's easy to peel off. Yes. Let's talk about acrylic. Acrylic is our acrylic adhesive. It includes water-based and oil-based. In fact, water-based and oil-based. It's just that the two have different production polymerization methods. Water-based. The advantage of water-based is environmental protection. Its main body is polymerized in water. The monomer of acrylic. What is monomer? What is monomer? A monomer is a small molecule. Are small molecules before forming the polymer. Under certain initiators or heating conditions, it polymerizes into a polymer. Its main body needs to be in water. In water, it can also maintain a stable and controlled state. It can also dissipate heat. Because it needs to be heated, it is exothermic during the polymerization process. But when it forms in water, the monomer itself is oily. It's actually oil-based. In fact, it cannot be dissolved in water. So we need to find a way to make it dissolve in water. We need to add some surfactants, which is similar to soap, such as soap, which is a surfactant. It has both polarity and non-polarity properties. So some additives will be added here. These additives will affect its subsequent performance. These surfactants are originally hydrophilic, so it's a water glue. The weather resistance of water glue, especially water resistance and alkali resistance, is far inferior to hot glue and oil glue. That is the essence of it. It is polymerized in water. There are some residues of some surfactants are left in it. Its biggest feature is low environmental cost. And it's water-based glue. Water-based adhesives generally do not attackifying resins, so its viscosity also has an upper limit. The upper limit is small. It is generally difficult to exceed 18 or 20 newtons. The oil glue is polymerized in the solvent. The solvent, organic solvent, is not environmentally friendly. But in the polymerization process of oil glue, it is relatively pure, because after coating, after the solvent evaporates, only the glue is left, without any other additives, and the polymerization process is relatively easy to control, and easy to design. Just like many single products, even if it is emulsified, can't be added to water. The designability of oil glue here. Its range is relatively wide, such as high performance, high, or some high strength ones. You can only choose oil glue. There is no way to control its environmental friendliness. If you want particularly good performance, it's linear. And oil glue will also add a curing agent. The curing agent is a very important thing. You can't just have glue, just glue. It is a long chain flexible thing. It can flow, so it's not good for holding power. You must add a curing agent. Before adding the curing agent, the structure of the polymer is like this. Linear. It's linear. Curing agent. I have an active group here to connect here and here. It forms an irregular network structure. The overall strength is improved. For this structure, if you apply high temperature to it, it will still be relatively tight, unlike water glue or hot melt glue. Without curing agent, which are easy to flow at high temperatures, it's not easy to keep stable. After adding the curing agent, even at over 100 degrees, it can still maintain its stability and some weather resistance, and outdoor and ultraviolet resistance, all of which are necessary. Today, I will only do some basic explanations. The inks, printing problems, and coating problems. We will discuss them in detail later. Today, we mainly talk about the basics.